Okay. Jagannath, am I audible? Good evening, Jagannath.
Yes, sir, you're audible.
Okay, good. I'm starting the session now. Okay, full screen. So, hello and good evening, everyone present here. I'm Shouharda Ghosh, a first year PhD student in the Department of Electrical Engineering at IIT Gandhinagar. I've completed my BTech as well as MTech from IIT Kharagpur in the field of microelectronics and VLSI design, electronics and electrical communication engineering. And welcome to this PMRF session on real-time digital signal processing. This is week 9 and we shall get started. This session shall be much shorter than the earlier sessions because we don't have much mathematics to discuss in this one, not much concepts involved, just applications, and they're just simple applications of whatever we have learned so far in real life. And if you even look at this week's assignments, they are mostly knowledge based questions. So there's the only way in which you'll be able to answer them is to look at the lectures and then get the so-called theoretical knowledge clear. There's not no much of rigorous concepts involved in this session, in this week's module, as well as the further upcoming modules as well. Okay, so is the screen visible?
Yes, sir.
Okay, fine. So at first we shall be talking about graphic equalizers. Okay, so I shall be this will be much of a one-sided information based session because I'll be stating some important top terms and terminologies and the definition in this case. So where do we find what are graphic equalizers and where do we find them? So basically equalizers are used in home sound systems, studios, concerts, etc. There they are used, there is a main application used to boost or attenuate certain portions of the audio spectrum for making changes in the sound aesthetically. So you might be thinking that are we again doing filtering again? In this case it's a special kind of filtering. For example, there's there's music and song. So in some cases some people like to decrease the bass content. There are, you might have heard about bass, treble, and high frequency and bass, treble, and mid. These three terms are frequently used in music systems. So depending on one's liking, somebody may make the treble high. The treble means the higher frequencies, so that makes the sharper high pitched tones more clearer. Some may want the bass to be higher, which is the low frequencies. Some may want the mid frequencies higher. So that's what you do, either boost some of them or you attenuate the other. Okay, so what are the kinds of equalizers? Remember, this portion is very less of signal processing and more of application consumer electronics, tone control, graphic console, and parametry. Okay, so a graphic equalizer So a graphic equalizer, or what we'll write in short as GE. What is this GE? G is a tool for independently adjusting the gain of multiple frequency regions in an audio signal. So common graphic equalizer designs provide up to 30 controls for manipulating the frequency response of each audio channel. Okay, so after since this session will end up quite early, so in case you have some doubts from previous modules, you may ask me after this is over. Okay, each audio channel. So what is it actually? Structurally, it is a set of filters, each with a fixed center frequency and bandwidth. So note this term very carefully, that the center frequency and bandwidth of all the filters are fixed. It's very important. The frequencies cannot be changed. It's not an adaptive filter, it's a fixed frequency response filter. Bandwidth. So what is variable? The only user control is the command gain, or the amount of boost or attenuation in each frequency band, which is often controlled with vertical sliders. For example, in your computer or somewhere in your music system, digital music system, you must have seen some kind of sliders, like mentioning bass, treble, mid. Okay, and there are some sliders with lots of scales, and the scales are in dB. Says -0, -30, -60, -90. Okay, same goes over here, 0, -30. So I'm just mentioning them as arbitrary numbers, but they can be something else as well, and these are often standardized depending on requirement. And you have some kind of a slider like this, which you can move up and down. Okay, similarly, let me draw one over there. Sorry for the bad handwriting. Okay, clear? These are the sliders, and at these I am showing as 3 digits, but there can be more and more depending on the complexity of your system. You can have higher and higher number of regions to control. Okay, so in fact, some digital audio systems in smartphones have several preset settings for graphic equalizer for music styles like pop, rock, jazz, etc. You must have seen this in your music systems, where you can click on the kind of background you may want to create a concert kind of. You get some options like concert hall or underground studio. Okay, so these are, so you might, if you play around, you will be able to get with different settings. So what it invariably does is that it changes the frequency response of the filters in each of the audio bands. Okay, so whatever I've been telling till now, so it's implemented using a cascade of equalization filters or a bank of band pass filters. And what are the common designs? Some say the one is the octave design, one is the 1/3 octave design. Okay, so I'm not discussing much over here. So it's like bands keep doubling in frequency, and here one octave has 3 bands, so this one is a bit more sophisticated than the normal octave. Okay, so that's some of the basic theoretical stuff about your graphic equalizers. Okay, really pure theory. Okay, then you have the design. Okay, so GE design in cascade, how does it look like? So you have an input, you have an overall gain G0, so it's like your volume button, low, up, high or low. Then you have the first filter, you have the second filter, you have m such filters. Okay, and then you get the output. And as I mentioned, all your filters are fixed in frequency response, but their gains are variable, so we call it an accurate cascade graphic equalizer. Okay, and how can each, let's say in the ith filter look like? So it's a bichord filter. And how does a bichord filter look like? This is a very familiar structure. I'm sure by now you all are familiar with it, because we have done lots of assignments with these structures. The delay elements, then the gain elements, similarly out, A1 of M, A2 of M, B1 of M, B2 of M. We also call it a second order section. Okay, it should be, the O should be capital, it's not save our souls. It's a second order section. because the denominator has two poles, okay, because a1 mz inverse and a minus a2m z to the power minus 2, okay, and one band has one filter. So in a standard 10 octave graphic equalizer, we have 10 filters, okay. And now let me show how does the filter response actually look like individually. So the first filter h1 of z, which is to the extreme left, it will be a low pass filter, okay. The second filter will be, and I am giving them variable gains, okay. This, let's say, the second one, then this will be our third one. So these are tunable. Actually I am giving for certain some configuration the user has done like this, so it may look like this. This is the first, second, third, fourth, fifth, sixth, and seventh. Oh sorry, same color. What color should I choose? Okay, let me choose this. Let me write the names down. h1 of z, its gain is a1, a2, h2 of z, a3, h3 of z, a4, h4 of z, a5, h5 of z, a6, h6 of z, and a7, h7 of z. So how does the overall response look like? So it's a1, then it goes up like a2, goes high a3, a4, a5, a6, and a7, okay. So this is the overall response, and this is the individual response of all the individual filters, okay. So when you're cascading them, it's like set of, you're multiplying all the responses, okay. And this was the cascade design. So how does it look like in the parallel version? GE design in parallel input. So all the filters as well as the gains G0 get the same input, okay. H1 of Z, G1, H2 of Z, G2, HM of Z, GM. All filters receive same input. So what is the advantage of this? the advantage of this is that when you have to consider, when you will do the design of such filters, then you need to consider the range of values these signals attain. Okay, so when you do cascade, then you may have a condition scenario, where let's say this one amplifies your signal by a factor of 2, this one amplifies your signal by a factor of 10, then so on. So the next one will be by 20. So if in case it you have set the gains in such a manner that it keeps on and amplifying all the values, then what will happen, the corresponding bit widths inside our filter will also keep on increasing. Okay, so as you keep on going in this direction, you have to use larger and larger bit widths. Okay, and so that makes our circuit much more area consuming and power consuming, and that is not what we want. So if we do see the same input is going over all over here, so what will happen is that since the range of the inputs are the same, so all of them will have the same kind of input output bit width lengths. Okay, so that makes the filter design easier in terms of the bit width selection of the input output as well as the internal signals. The only thing that will vary is the adders. Okay, the adders over here will be much wider. Okay, in that previous case there were no adders, as you can see over here, but here the adders will have larger bits in order to accommodate the maximum dynamic range of the signals involved. Okay, so that's about your basic graphic equalizer. Then we will talk about okay, sorry, now I'll talk about 3-band equalizer. Okay, it's a simpler version of the original equalizers that we have seen. The 3-band tone control was designed with frequencies of 200 Hertz low shelf, which is the lower limit of the hearing audible range. Sorry, that's 20 kilohertz, but then our speaking range. Then 1 kilohertz mid peak, quality factor equal to 1. So band pass filters are characterized by the bandwidth as well as the center frequency. So what is quality factor? Quality factor is ratio of the peak frequency to the bandwidth. So the fc by delta f, so that's your quality factor. And 5 kilohertz high shelf. Okay, so how does it but then the kind of diagram that was given in the class lecture was a bit different. Okay, so what we had was the gain in dB 0 plus 6 plus 12 minus 6 minus 12. Okay, this is the low pass filter with cutoff fc1. Okay, bandwidth does not make sense in a low pass filter. Then you have the first band, here also your cutoff is fc2 and let's say the bandwidth is fb. So these levels show the choices that you have in the choices of the gain in each of the band. So you can choose 0 dB, which is as it is, 6 dB gain, 12 dB gain, or 6 dB attenuation, 12 dB attenuation, something like that. Similarly, you have another mid peak range. Okay, here also you have the same choices of the gains, and similarly This also has a peak of FC3 center frequency, bandwidth FB, and a high pass filter with cutoff FC4, frequency versus gain plot. Okay, so 1 2 3 4 5, 1 2 3 4 5. So there are actually 5 to the power 4, which is how much? 625 choices of frequency response. Okay, so that this 625 doesn't make sense, but I wanted to show you an idea of how using just you have kept the filters fixed. Okay, but then just using the gain knobs you can get a good variety of frequency responses. So from a block diagram view, X, the Xn is input signal, undergoes low pass filter shelf, then mid frequency low frequency shelf, mid frequency one peak, this one, then second mid frequency this peak, and then the high frequency shelf. Then you get your output Yn. So it's a part of your input signal going to a to D converter, then it goes to your its audio signal, then you have your equalizer, then okay you have your discrete digital signals Xn and Yn. You go to a DAC and get back your original signal. Okay, so this portion actually comes into your equalizer. Okay, so we have now completed equalizers. So any doubt in this? Do you have any doubt in this?
No, sir.
Okay, fine. So now we will cover two more topics. The first one is echo. Okay, so what is an echo? Echo is reflection of sound from solid surfaces. Okay, so how does it happen? So when a person speaks, so it emits sound waves. Okay, and it undergoes reflections and he hears back. Okay, the shortest one, let me highlight it with a different color. Actually there are multiple paths possible. Okay, so basically when you talk about echo, it is the direct path or the shortest path one that I have shown by the green color. So this is actually causing an echo. Okay, so when you have an echo, so how do we represent it in a signals and systems perspective? So basically we say that the output is equal to the input plus the actually when it travels in the medium, it and due to certain physical phenomena, due to damping in the air medium and other factors, it undergoes losses. Okay, it undergoes loss, and what undergoes loss? The delayed input. Okay, so how can we write it as yt equals x of t plus a into x of t minus tau. Tau is your delay. Okay, and note that in human beings we cannot distinguish between echo and original sound if tau is less than 0.1 second. Okay, so you need at least 100 milliseconds of delay in order to be able to get a good echo. Okay, that's why when you speak in the room, we don't get our echoes normally, because the reflections are coming very fast. So in fact, if we try to discretize it, what we get? Yn is equal to xn plus a x of n minus n naught. So what is this n naught over here? N naught into the sampling rate of our system, ts is tau. Okay, so that's the ts is sampling period. Okay, so how does it look like? So you have xn, you have again, actually it's a loss followed by a delay and then an addition. Okay, so it's not a simple deal, just a one sample delay, it's an n naught sample delay. Okay, so we add them and we get yn. So you observe that it's an FIR filter kind of a response. Okay, so basically you can use an FIR you can use this simple FIR filter to emulate or to emulate the echo. Okay, so if you want to use if you want to give an echo kind of a tune or some sound effect in any of your recordings, then you can simply program an FIR, simply code in an FIR filter into your computer, in your system, and you can generate echoes. As simple as that. Okay, okay, now we talk about the last topic of our session, that is reverberation. Okay, so what is reverberation? It is the persistence of sound in a particular space after the original sound is removed. So when is it observed? A reverb is observed when a sound is created in an enclosed space, causing multiple echoes to build up and then slowly decay as the sound is damped by the surrounding surrounding and air. It is the sum of all sound reflections. It is most noticeable when the sound source stops, but the reflections continue, decreasing in amplitude until they can no longer be heard. Okay, so how does this echo differ from a reverb? It differ from a echo. Okay, so let's suppose I give an input sine wave at an instant of time. It's not a sine wave, an impulse. Okay, so this is my direct sound. So the one that I get immediately after is my earliest reflection. Okay, following this I have a few more reflections, and then after the last distinct reflection we get to hear the voice for a long time, comparatively long time. So we get a continuous kind of a hum, and that's the reverberation. So let me distinguish this. These are early reflection, and these are your late reflection. Let me designate two timelines, tau 1 and tau 2. I call tau 1 as pre-delay, and I call tau 2 as reverberation time. So how can I model this reverberation? So basically let me write it down in words first. So in a reverb, the output is actually the input plus the loss times the delayed output. So here comes the difference. Over here we are seeing the output, but the delayed version. So in terms of continuous time, how can I write yt equal to xt plus a into y of t minus tau. So I hope you are not able to guess where we are heading towards. Okay, now what kind of a filter does it look like? Yn equal to xn plus a yn minus n naught. This is nothing but an IIR filter. Okay, that's why you get this kind of an, that's why it's an infinite impulse response. See, it's lasts for a long time, but then it actually lasts long, but but the intensity fades to an extent that your human ear is not able to perceive this sound at all. But in the case of echoes, the direct reflections or the real reflections, there are a finite number of them. You see, one, the original sound, that's a delta t, then the second, the third and fourth and the fifth. That's it. It's a finite impulse response, and then you have an infinite long impulse response. That's the reverberation. Okay, so how you can model this? In fact, this reverberation can be heard in audio concerts as well, and you can emulate that in your system, in your mobile phone or in computer, using and coding an IIR filter. That's it. So you have a xn, you have yn, you have some factor gain, then a delay of n naught samples, and you add this to your output. That's how you model your, just over here this is an IIR filter. This is simply how you model a reverberation. Fine. So we have completed this week's module. So this was a quite short module in this week. So do you have any doubts regarding any of the concepts or the theoretical points that I have mentioned, or anything else from the module? Jagannath, are you there?
Yes, sir. I have no doubts, but can I ask, is this the last this one
Mm,
problem solving session?
no, this is a 12-week course basically. So you have week 10, week 11, and week 12, and apart from that, we will have another session that will be a 1 hour session. Actually, the later sessions will actually be very small. So theoretically, it's 2 hours, but it will be another session which will be completely a small revision recap of whatever you have covered in all the 12 weeks. Okay, so in practice so we have week 10, week 11, week 12, and a recap or a revision session. So we have 4 sessions left. So you have this course is actually a 12-week course. So if this had been an 8 week course, so this session wouldn't have taken place. So two, actually that 2 hours, but then just like today's session, the next sessions also might be smaller. I have to check. And this revision session will be a 1 hour session for sure.
Okay, sir. Thank you, sir.
So do you have any doubts regarding um, okay, you said you have no doubts now
Yeah,
for
I
the
haven't caught up with recent sessions, so I have to catch up with it and yes,
okay.
come up with few doubts later on.
Okay, so let me um, try to check the previous year's session, previous year problems. Just hold on a second, let me share the screen. So, is my Google Chrome visible?
No, sir.
Oh, my entire screen share, dismiss. Oh, fine. For some reason, let me. Okay, for some reason they're not allowing me to even access the screen. Why? Okay, so what I can see over here is most of the questions are part of the present previous ones and the present session as well. And if I look at the previous year, you will be able to see my Google screen in the recorded version. So let me check once. So by the way, apart from this course, are you taking any other course on NPTEL?
No, sir. Not right now.
Okay, okay.
Sir, previous year question papers are available, is it, in NPTEL?
That's not acha. So actually these sessions are for that reason only. So let me check the questions that were asked previous year. Okay, so let me mention the question. Okay, so let me directly write some of the questions. Is my uh, this thing visible? Okay, no, fine. Let me write this. Actually, in the record, in those who will be seeing the recording will be able to directly see the assignment questions as well as the answers. So I'm writing down for your convenience. So some of the questions related to this topic in the previous year, like if ITU T.G.7 to 9 processing signals. So these are all some conventional standards, like we have ISO and ISI, IEEE. So these are also standards. ITU, International Telecommunication Union, signals in 10 millisecond frames and a 5 millisecond look ahead. The total G.729 algorithmic delay is, first option is 10 milliseconds, second option is 5 milliseconds, third option is 15 milliseconds, and D is 30 milliseconds. Okay, so over here they have mentioned the correct answer as 15 milliseconds, and it's obvious because total delay, this total algorithmic delay, whatever data machining, is 10 milliseconds plus 5 milliseconds. It's simple. That's your first question. Number 2, G.729 compresses speech from 16-bit 8 kilohertz samples to, first option they've given as 8 kbps, second option they're given as 16 kbps, third option was 128 kbps. Okay, so they have actually A and D are actually they have given same option and they have mentioned 8 kbps as the correct answer. So basically it's just a knowledge based question, but then what is actually happening is that if you look at the original sample rate, so it's 16 to 8, it was originally 128 kbps, but then due to using speech compression or speech coding, which we will be doing in next week, so they use this to 8 kbps. So in communication systems you may have learned about lossless compression, lossy compression. Okay, so they use compression techniques to reduce this. Okay, so they've given some picture as well. Okay, so all the questions are more of okay, so most of the questions are purely knowledge based and theoretical. It's not much of solving. So for example, there's a question, let me mention one. It says the various filters in equalizers allow you to a adjust or gain the frequency ranges of audio signals, adjust or gain the time of audio signals only gain of the frequency range of speech signal and the adjust or gain the frequency range of video signals. So the correct answer that is given is option A, and that's quite obvious because there's audio signals, and in the other case time of audio signals does not make sense, and here it's given only gain of speech signal. Here they have given speech signals, so equalizers are used in music systems, so speech plus music, and this is video signal, so it does not make sense over here, so option A is correct. So these are some of the questions, and like they have mentioned another question, overdoing of bass adjustments. Now what does it do? Option first, music becomes more clear. Option 2, music will be distorted. 3, music is not affected. Option 4, treble will be affected. Okay, so the correct answer that is given is option 2, music will be distorted. It's obvious. Why? Because if you do too much of bass, if you have tried it out, then the low frequency sounds will dominate to such a huge extent that you will not be able to get the essence of the high frequency tones of the music. So let's say guitar, piano, violin, so all the high frequency notes will be in a low, will have low amplitude compared to the bass or the human speech, that speech one, so that will make the music too bad. So overdoing any of the settings will actually make things worse. Okay, so there they are given some of diagrams as well. It's not much of it. So okay, so you say saying that there's no doubt from your side as of now. Fine.
Yes, sir.
Okay then. So I think we can conclude then. Jagannath, can you conclude then? Hello, am I audible now?
Yes, sir. Audible.
Yeah, so can I conclude now?
Yes, sir. Yes.
Okay then. Okay, so thank you everyone for attending this session. So we'll meet you in week 10. Goodbye.